Okay, so in this research, what we're trying to do is automatically and speculatively parallelize loops in the program using the result from the polyhedral dependence analysis. So polyhedral dependence analysis gives you different kind of dependencies in the program. This can be may dependence, must dependence, or no dependence. So what a normal auto parallelizer like OpenMP parallelizer will do is it will see the different dependencies inside loop. And if it finds out that there is no may or must dependence in the loop, it will parallelize the loop. But we are trying to be more greedy. We are trying to allow loops with may dependencies to execute in parallel and see if we can get any performance improvement. So the question is why we want to do it. Because auto parallelization is good, but the dependencies in the program prevents the parallelism. And we need a sophisticated dependence analysis that can tell us about the different may, must dependencies in the program more precisely. And as I've said before, auto OpenMP will only parallelize loop where there is no may dependencies or must dependencies. So can we do better? Can we try to extract more parallelization from the program? So here's your polyhedral model, which is more powerful than the normal static dependence analysis of techniques you have. And in the polyhedral model, every statement instance is represented as a point in an integer polyhedron. And in this way, what a normal static dependence analysis will do is it will take a statement inside a loop and it will consider all the instances, execution instances of that statement at a time. But polyhedral model doesn't do it. For every iteration of the loop, each execution instance of that statement will be considered separately. And thus it can reason more about the different statements inside the loop. It works on scopes, or what we call static control parts, and these are normally loops with special features, like the loop has to be in canonical form, it shouldn't have any early exit conditions inside its body, and there you have thread level speculation. So what is that? In TLS, or thread level speculation, you can execute program parts in parallel even in the presence of a dependence. How do you do it? They have special hardware or software mechanism that support and guarantees correct output. So even if you have a may dependence inside loop that you don't know whether that will be materialized in runtime, but still you can execute that loop in parallel with the hope that that will not materialize at runtime, and even if it does, it will have special support to guarantee you correct output. But still we need a good dependence analysis. Why? Because TLS has overheads. There is overhead for thread creation, and there is also overhead in case of misspeculation. For thread creation, you have to store the program state inside registers so that the program can be rolled back to a previous consistent state in case of a failure. And in case of misspeculation, what you have is you have done some work in parallel, but then it's lost because you have done the wrong thing in case of a dependence. So in that way, you are losing the work you have already done, and you have to then execute that in maybe sequential order. So there's overhead for misspeculation also. As I've said before, thread creation as overhead. And if we have polyhedral analysis, which is powerful enough, and TLS, which has support for may dependencies as well, so we are having like power of two superheroes. So here's this Poly. Poly is a polyhedral optimizer which is implemented in LLVM, and it has different passes. Like the polyscopes pass discovers different scopes in the program. Scopes are loops, by the way, with some specific properties. And there is also a built-in dependence analysis pass that can tell you whether there are may dependencies or must dependencies inside the loop. It also has auto OpenMP support. So if it finds out for a scope there is only no dependencies, there is no must dependence, there is no may dependence, then it will insert the OpenMP runtime calls inside the code, and thus it will parallelize the loops. So it's the same old question with TLS hardware in hand, can we be more greedy, right? So there are the research questions which we try to answer. The first one is, could polyhedral dependence analysis find loops or scopes that are candidates for TLS? Will the TLS execution of loops with made dependencies result in performance improvements? So if we be more greedy and allow loops with made dependencies, will that give us any performance improvement? And the third question is, can we go better? Can we, with the help of profiling, actually see whether the made dependencies are occurring at runtime, or we can eliminate the loops which has very less execution time as compared to the whole program, what we called cold loops. So if you execute the cold loops in parallel, the thread creation overhead is so much that you don't have much work to do inside the loop, and that's why you get maybe a slowdown. You never know. So here's the first heuristic what we use. It's very simple. The first one is, if there are only made dependencies, parallelize the loop. We don't care whether the dependencies are occurring at runtime. We just do it with the hope that that dependence will not materialize at runtime and we will get some performance improvement. And in the first heuristic, we also don't filter out cold loops. That'll be done in later. So here, it's not powerful enough because we are not doing it wisely, but still we are getting more speculation candidates than OpenMP. And if we get lucky, we'll get some speed up. Here's a heuristic 2, where we consider the two TLS overheads. The first one is the thread creation overhead, which I've mentioned before, and the second one is the misspeculation overhead. For thread creation overhead, we filter out cold loops, and for misspeculation overhead, we profile for a training run and see whether the made dependencies are occurring at runtime. And if it does occur, we don't parallelize the loop. If it doesn't occur, we parallelize the loop. Oh yeah, use profiling to find made dependencies occurring at runtime. Okay, now comes our framework. Here's your test.c. We are doing source code annotation here because we didn't have access to the actual TLS runtime routines. So we couldn't instrument the bit code of the compiler with the calls to the runtime function as OpenMP does. So what we are doing is, before loops, we're inserting this pragma, which is called hash pragma speculative for, which is specific to the BG-XLC compiler, which is the IBM XLC compiler for the BlueGene machine. And yeah, we are doing source code instrumentation. So here's your LLVM with poly support. You fed that source code to the LLVM, and you run a pass which prints out the different basic block information. And what is the information? Where does this basic block belong in the source code, like the source file name and the line number? We'll be needing that because we are doing source code instrumentation. So this block, this pass prints out the different information about basic blocks. You also run the poly dependencies pass that gives you two different things. The first one gives you scopes, and the second one gives you the different may and must dependencies or no dependencies inside these scopes. So here we have blocks, basic blocks, and their source code, source file name and line number. Then you have scopes, which will have the different basic blocks in it, like which scope is consisted of which basic blocks. And then you have scopes with the may and must dependence information. So we do a three-way mapping between these three information using one script, and it prints out the different, it does a cost analysis, like whether there is any may dependencies or there are only must dependencies. And then it produces a file, what we call insert info, which consists the source code, the source file name and the line number where you have to insert the pragma. We run a script, and the script produces a source code annotated with the TLS pragmas. And then we compile using the XLC compiler, and we get the optimized executable test spec. So here's how our framework works. Now we come to the experimental evaluation part. So we are using two different benchmarks. First one is Spec 2006 because it's widely used in TLS literature before. and polybench C, which is because we are dealing with polyhedral model, so we need this benchmark. The platform is the IBM Blue Gene Q supercomputer, of course. It has TLS and transactional memory support, which is TM. Our baseline for comparison is the sequential version of the code with the O0, that's the lowest optimization level of the compiler. So in that way, we make sure that the automatic vectorization and the other loop unrolling and those kind of optimizations of the loops are turned off. And for TLS, as I've said before, we are inserting a pragma, which is called #pragma speculative for. And to try with different number of threads for TLS, we use this num threads option to the TLS pragma. The configuration of the Blue Gene Q chip, it has 16 processors per node, and each processor is 4-way multi-threaded. The clock is 1.6 gigahertz. We have 16 KB L1 I and D cache. We have 16 gig of RAM. It supports TLS and TM with the help of multi-version cache. So it stores different versions of the same value inside the cache, which is accessed by different threads. And the L2 cache is 32 megabyte centrally shared. And the networking is 5D torus topology. So here you go. After we use the heuristic one, we get some speedups inside some benchmarks. So that means that we are getting lucky in some benchmarks. Like for LBM, you have a huge performance improvement. Why? Because there is a huge loop which is hot enough, and the May dependencies, which are reported by the compiler by the polyhedral dependence analysis, doesn't materialize at runtime. So that's how we get the performance improvement here. But for GoBMK and SGeng, as you can see here, we get a slowdown. Why? For GoBMK, what is happening is we have very small loops which are executed in parallel. So they are called loops. And for SGeng, the main dependencies are actually turning out to be occurring at runtime, and that's how you get the slowdown. Then there is your polybench.c. For first 1, 2, 3, 4, 5, 6 benchmarks, you get a huge performance improvement on a 12-thread TLS. But over the last 5 benchmarks, again, we have lots and lots of cold loops, and that's why we are getting slowdown. Then there is our comparison with AutoOpenMP, which is done by the Poly. In this benchmark, and which I believe is, alright, these are not aligned properly, but they're aligned in the slides. Sorry for here, for some reason it's not showing up. So for these two benchmarks, whatever they are, there we don't find new loops than OpenMP. So they give the same performance as OpenMP. For LBM, of course, we're trying to find more loops than OpenMP, and then that's why we're getting this performance improvement. But for GoBMK and SGeng, for the reasons mentioned before, we're getting slowdown. Same is the case of polybench.c. Sorry for this. I should have fixed that, but anyway. So for the last 5 benchmarks, we're again getting slowdowns because they consist of code loops. For these two benchmarks, which are basically matrix multiplication benchmarks, and here OpenMP already does a good job. So we are not able to find more loops than OpenMP, and that's why we get the same performance as OpenMP. Then comes our heuristic 2. We have modified heuristic 1 to filter out cold loops and filter out loops with May dependencies that occur at runtime. Okay, we are not getting slowdowns, good news, but still we are not beating OpenMP. For some benchmarks, we are getting the same performance improvement, but for some benchmarks like Gram-Schmidt and SGeng, we are still getting better performance than OpenMP because we have filtered out cold loops that was putting us down, right? Okay, there comes the scalability. So we have run from 2 threads to 64 threads for the TLS, and in a Blue Gene Q, one compute node has 16 cores, and each core is 4-way multi-threaded. So for getting 64 threads, you don't have to go to one more node. So if you are still inside one node, you're getting 64 threads. So there is no inter-node communication here, but there is inter-core communication. LBM scales pretty well. As you can see here, it goes right above here, but for more than 16 cores, it kind of stabilizes. If you can see Sphinx 3, which is here, the performance doesn't change for increasing number of cores. It kind of is similar for all the number of cores. Let's suppose the reason is for Sphinx 3, we didn't find much loops for TLS execution, and so the speed up we are getting is kind of stable. For MCF, here you can see there is a slowdown from more than 8 cores, and for what is this, NumD, you're getting a slowdown for more than 16 cores. This is because of the fact that for these benchmarks, for increasing number of cores, there's inter-core communication, and that kind of increases when you increase the number of cores, and that's why you get the slowdown. Alright, so here we come to the conclusion. The first one is the result of the polyhedral dependence analysis can be used to find speculation candidates. Relaxing the constraint of OpenMP, like executing loops with many dependencies, also can give you performance improvement if the loops you are considering are hot enough, and also the loops with many dependencies doesn't materialize at runtime, and that's how you don't get a misspeculation. So that's LBM, which gave you lots of performance improvement there. But still, we could do better, and we have done better. We have modified the heuristic to filter out cold loops, which are not good speculation candidates. And also we have filtered out loops where many dependencies are materializing at runtime. And that's where we get equal or better performance than OpenMP, because we are filtering out not profitable loops. So for future work, we did the baseline for this research was the lowest optimization level of the compiler, because we were not considering the effect of vectorization by the compiler, which is done at higher optimization levels. So we are still performing experiments with 05 level of the compiler, which turns on the syndization. And also, there's this research work by one of the members of our group, which have shown that the program's behavior changes for different inputs. And they have proposed a method called combined profiling, which actually combines the different profiles which is got from different runs with different inputs, and you combine those profiles using histograms, and then you can see the probability of a main dependence that occurring at runtime. Like for example, the main dependencies may materialize for some inputs and may not materialize for some inputs. So you have the probability of the main dependencies materializing at runtime, and based on the probability you can come up with a cost model, and that can give you candidates for TLS. But for the benchmarks, which was used before in the literature, and we have also run some more benchmarks, at least 50 or 60 of them, and they have shown that the loop's dependence behavior doesn't change for inputs. Like the loops which are candidates for TLS, their dependence behavior didn't change at all. They're either parallel or independent for all the inputs they have run. But still, you can think of programs where there will be loops and whose dependence behavior will change according to different inputs. We are still trying to figure out those kind of loops that can occur in different benchmarks, and we are still in the process of writing our own benchmarks which will have those kind of loops inside them. So yeah, that's the plan of the future work. Any questions or comments? Surely you'll have questions. Thank you.